Okay. Um, so so as you can see, I'm Boya from the University of Pennsylvania. Today I will share with you a bit about understanding bias in large-scale visual data set. Um, but before everything, let's go back in time, like way before that moment of deep learning. One of the earlier and arguably most classic visual data set is MNIST. Datasets like MNIST are datasets that define a task. Since MNIST was proposed in 1998, we have been pushing the boundaries of computer vision, making more and more diverse datasets as a community. And so this leads to Cypher in 2009 and ImageNet same year. But what's unique for ImageNet is that the community discovered that the neural network representations learned on these large-scale datasets like ImageNet are transferable. So the discovery brought in a paradigm shift in computer vision. It became a common practice to pre-train these representations on like large-scale datasets like ImageNet and transfer them to downstream tasks. And ImageNet dataset was no longer a task of its own. It became a dataset for representation learning, or even higher on a higher level, it become a pinhole of the universal real world that we want to represent. Then on, the community began to pursue, more general and ideally universal visual representations. And fast forward to year 2025, the community has created a wide range of large visual data set with the purpose of pre-training. Three representative ones are YFCC, CC, and Datacom. We'll abbreviate them as YCD. And they are presumably among the most diverse, largest, and uncreated dataset in the world collected from the internet. Um, so given how comprehensive these smaller datasets are, we wonder, are they general enough to represent universal real world? So way back in 2011, Trobe and Erfros proposed the name that dataset experiment, which is a classification task where SVMs are trained to predict the dataset origin of images, just over datasets like smaller datasets like Contact 101 and Label Me. So the dataset like these back at the time, since you have different collection mechanism and sources, turned out to be classified very well with like 39% accuracy for a 12-week classification just from SVMs. Also, they found that like a model trained on one dataset can only perform well on that dataset, but fails to generalize to other datasets. So over the last decade that followed that paper, we have like made tremendous progress on building more diverse, large scale, comprehensive, and hopefully less biased datasets. And this progress has really been the engine that's powering the deep learning revolution. And also in parallel, we're not stopping at like SVMs. Advances in like algorithms, especially like neural network architectures, have achieved unprecedented level of ability in discovering concepts, abstractions, and or just patterns. And that could include the dataset bias um, that is originally proposed here. So with this tension between building more powerful models and building less bias and hopefully more general data sets. Um, if we take a look at this data set bias problem, like after this whole decade, we wonder like how much bias in these smaller data set can still be captured by these current neural networks. Oh, I'm missing my VS sign here. Okay. So again, here is the framework for the name that data set or just data set classification experiment in 2024. So we have our images that is randomly sampled from YFCC, CC, and Datacom. Again, like our large scale data sets of 2025. And we would train a neural network classifier to determine whether a random image here would come from YFCC, CC, or Datacom. And ideally, if the data sets are perfectly unbiased, we would hopefully expect a chance level accuracy of 33.3%. But as it turns out, modern neural networks can achieve excellent accuracy on such a dataset classification task. And the chance level, if you just guess, it will be 33.3%, as I said, but we get an accuracy of 84.7%. And this is not even just for this combination of 5CC, CC, and Datacom. It also for all the dataset combinations from like 5CC, CC, Datacom, Lion, WIT, and ImageNet. So this is certainly not just one instance here. And the accuracy, we get here is from the complex architectures. So models may have different architectures and inductive bias that would facilitate this accuracy, but none of them seem indispensable here because like all these neural network architectures across these all these neural networks across these architectures are found to be extremely good at capturing the dataset bias, as we can see from the accuracies here. And also, you want to know if like reaching like this high accuracy would like need a large model size, similar to like how what we're observing in like conventional visual recognition. And we're always saying like, okay, so the massive number of parameters is like a central driver for the success, but this does not seem to be the case here, as like even complex with as few as 7K parameters can achieve like 72.4% accuracy on data classification. And also another thing to check would be that like about training set size. So as shown here, the models trained with more data would achieve more validation accuracy. This would obviously seem very obvious in the semantic classification task, but this is not necessarily true for dataset classification that we're dealing with, because if the models were focusing on memorizing the training data, the generalization performance on the validation data might even go down. It would even decrease. But this observed trend of more training data improves validation accuracy, suggests that the model is learning certain meaningful patterns that are generalizable to unseen data rather than just memorizing or overfitting the training data that we have. And also, data augmentation would be expected to have like a similar effects as what we're doing here, introducing the training set size. So adding data augmentation would make it more difficult to memorize the training images since they introduce a lot of variations. Um, and we observe that like using stronger data augmentation would consistently improve the data set classification accuracy, again, similar to like adding more data. So this mirrors the observations we get from semantic classification or just classification with semantic classes. Um, so this suggests that like this classification is approached not through memorization, but by learning some generalizable patterns from the training set that can also be applied to the validation set. And for comparison, if the samples of like different architecture were unbiasedly drawn from the same distribution, the model should not discover any like dataset specific bias. To just check this, we can just literally construct like pseudo datasets by just sampling images from the same actual dataset, and like we would perform like a pseudo dataset classification task on these like pseudo datasets that we get here. And so the only way for like the classifier to approach this task would be to memorize every single instance and like which subset it belongs to. So the model, as we expected, quickly fails when there's like more training data or augmentation, like when there's like 100K images or we have like strong augmentations applied to the images. Also, um, also note like we're actually just showing the training accuracy here because um the test accuracy is always just chance level since the model cannot learn any generalizable pattern from the training set. Okay, so it is still unclear here what dataset classification is actually learning. So we can try to look into the features learned by classifying these datasets, by using this dataset classification as a sort of pretext task. And after like doing this training, we would perform linear probing on the frozen features of this dataset classifier on a semantic classification task. We're just like image at 1K classification. And you see we have like on these lines here, we have like YC and D and YCD plus like width and log image set with all these sort of different combinations of data classification to serve as the pretext text. Um, so yeah, so my bad. Compared with the baseline of just using random weight and doing linear probing on there, the data classification model can actually result in like non-trivial image at 1K linear probing accuracy. And also, as we observe, very importantly, using a combination of more data sets can increase the linear probing accuracy. So like better features are learned by discovering the data set bias across more data sets. And well, admittedly, like the data sets features that we're learning here are indeed not as good as like self-supervised learning objectives like MAE and local V3, but this experiment still shows that like this bias captured by these neural networks is indeed relevant to the semantic features that are useful for image classification or just image at 1K classification. Yeah. Okay, so now that we know this, there's a question that remains. So what are the concrete forms of visual bias among these data sets? So to look into this, we apply various transformations to extract different types of information from the data sets and then perform this same data set classification task on the transformed images. Um, so like we could do semantic segmentation to get the semantics component, and this sort of transformation plus classification paradigm would help us understand how each type of information contribute to the dataset bias. Okay, so let's start from semantic segmentation mask. It provides like fine-grained semantic annotation, but removes texture that might hint at the dataset identity. So the dataset classification accuracy just on these colored masks could show how like semantically biased these datasets are. So it turns out semantic segmentation mask gets us a classification accuracy of 67%, which is lower than the 82% on the original images, but it's still significantly better than chance. But like, what if we completely just remove the visual information, like including all the textures and also like the spatial information that is still present in semantic segmentation mask, and like just use VLM generated captions to represent the semantics, and we would just fine tune a sentence embedding model to perform this caption classification task. And like captions are will be less affected by pixel variations than like some spatial cues in the image format. And the accuracies are similarly high for like this short version of caption and long version of caption that we're just prompting the VLMs to generate with. So like this richer detail in these longer captions would enhance like the performance. So also on top of these transformations that seek to preserve semantics, we also try to like use a VAE to hopefully remove the low level signatures. You can think of like JPEG compression and like color quantization. So after like applying VAE to the images and performing the classification on the resulting images, this does not really decrease the accuracy much from the original 82% on original images. Um, so low level bias, like JPEG compression or color quantization, may have like a smaller impact than semantic bias. Okay, so these high data classification accuracies on semantics tells us that semantic bias is an important component of data set bias that we're observing in these smaller data sets. So up next, we analyze the data bias and object shapes. So we can use segment anything model to generate class agnostic segmentation maps, and then from there we can just outline, object boundaries. And this brings us to like a quite high accuracy of 73%. Um, and also, another way to look at like the structures in these images would be spatial geometry or just depth image. And if we just do the steps estimation and perform classification on the steps image, we can get an accuracy of 73%, which is still quite high. And so from here, we can know that like object shape and spatial variations are also like significant among like the YCD data sets that we're studying. And just to see further how like the bias is captured like spatial information versus the other components, we can just shuffle the pixels to completely disrupt the spatial coherence. So we either shuffle these image patches with a random order for any given image, or using a fixed order across all images. So as we kind of expect, the accuracy would drop a lot from the original 82%, but it's still like better than chance. So there's definitely not a non-negligible difference in the pixel value distribution in these images. But again, this may or may not just result from the semantic bias that we are observing for. But what's interesting is that if we divide the images into patches of size 16 and just shuffle the patches instead, the accuracy in fact doesn't go down from like the 82% on original images. Therefore, like completely destructing the local structure can largely reduce the dataset bias, and like these patch level local structures are suffices to identify the dataset bias. So now, what if we just like do the simplest thing and just average the RGB values across all pixels in an image? So this simple color statistics can still lead to like a non-trivial classification accuracy. And if we just look at like the distribution of like main RGB channel values across like all images, we can see that like the concrete line YCC is darker than CC and datacom. So another thing that's interesting to know is that synthetic images have great potential for like augmenting data. We're seeing it being applied to like all these domains and all these sort of generated models. Um, so we want to know if like dataset bias can be inherited from like diffusion models training images to as generated images. So we trained one unconditional diffusion model, DIT, on each dataset and try to classify the generated images from these individually trained unconditional diffusion model. And it turns out the generated images can also be classified very well. So the upshot here is that the synthetic image can indeed inherit the bias in the diffusion model's training images. And a potential implication of this is that these bias may persist and even amplify in downstream tasks that use generated images for training. We could also sample like synthetic images from a pre-trained text-to-image model based on the VLM captions of YCD images. And by converting these images into captions and then back to the image modality to work with a image classification model, this process only retains like the semantics that are captured in captions, and we're getting like a 58.1 accuracy, which is only a little bit lower than the accuracy of 62 that we get from captions themselves. So this accuracy further confirms that like semantic bias is a major contributor to the dataset bias that we're getting. So far, we find that semantic bias is very important in YCD datasets. How about like we go one step further and explain it in detail? So to this end, we analyze the semantic bias on the object level. So we apply models pre-trained on other vision benchmarks like image classification, Elvis object detection, 8020K segmentation to provide object annotation for each image. So here, very simple, we compute the number of images in each dataset that contain a particular object class. We can see that there is a considerable imbalance in like object level distributions across these datasets. So, for example, like more than 60% of images containing the Elvis class water bottle are from YFCC. So this sort of indicative like of the dataset identity of images that contain water bottle. So overall, YFCC emphasizes like objects that are related to outdoor infrastructures, while CC and Datacom like contain more images of household items and like product showcase. Also, the generated captions from Lava can also serve as like a semantic representation for the images. And from there, we can leverage like various natural language methods to analyze the datasets. So using classic topic discovery model on captions would let us find key concept for each dataset. We can see that like YFCC is mostly characterized by outdoor scenes, like street, car, sign, water, sky, tree, to name a few. And Datacom have more emphasis on digital graphic and static objects. We can also prompt like LMs to summarize each dataset's characteristic by providing it captions. So the generated output is shown here. And we were again seeing that, outdoor, natural, and human-related scenes are highlighted for YFCC, and static objects and digital graphics are representative of Datacom, and CC, on the other hand, blend both of their elements. So that's mostly all I have here. And so in summary, in the revisit of like the dataset classification tasks from 2011 was modern datasets and modern neural networks, we find that these bias can still be captured easily by these networks, and also such bias contains some generalizable and transferable patterns. And from there, we propose a framework to understand the concrete forms of bias in these large-scale datasets. And first, we use transformations to quantify, the bias that exists in each type of information in the images. And we then decompose the semantic bias with object and natural language analysis. We showcase our framework on these large-scale data sets that are representative these days, YFCC, CC, and Datacom. And I definitely encourage you to like check out our paper for more details and more experiments that are not covered in this talk. And so I also want to discuss like how we can potentially use like insights here to retrospectively analyze the data creation project process. So for instance, we found that like there are less diversity of object classes on average in the images in Datacom, and this could potentially be due to its filtering methods. Like since it is filtered based on like embedding distance to like image at images, this would likely prefer or just cause bias towards images that are resembling ImageNet, which are, as we know, like object centric. So Datacom resultingly would have like lower object counts, unique object count in its images, and also like um another very intuitive insight would be like, okay, so as we see from the analysis above, YFCC has like emphasis on outdoor and human related scenes, and this could likely just because it is sourcing its images from like a single data set like Flickr, and Flickr just have like user uploaded images, and like this would naturally feature more human interactions and outdoory kind of pictures, and also like CC and Datacom are web sourced, so they would naturally contain more digital graphics. And you'll definitely have to like decide on whether these are beneficial or suitable for your downstream use. And you can decide from there how you want to choose or create your own data sets. So yeah, that's basically it. And again, you're welcome to check out our paper and code with the QR code there.